Hello and welcome to this lecture on heat transfer. So in last lecture we finished the chapter number 3, that is convection, and I told you all the concepts related to convection, and the most importantly I told you the Nusselt number formula or relation for different cases like flow over flat plate, pipe flow, or flow through conduit. So this is very important. The values I have given, the experimental values and the formulas that you have to remember. So convection, so generally in convection subjective kind of problems are more predominant, means conventional type, like that are asked in IES mains examination. But in objective also there is a very high potential of questions. Like in the starting of convection chapter I discussed this kind of problem, if you remember. So this was plate, this was the stationary fluid and then moving fluid. So here we just have to balance the heat balance equation, that was Q conduction in solid equal to Q conduction in fluid equal to Q convection in liquids. So this is very important from the gate point of view, these kind of things, because the questions that are originating from these Nusselt number formulas, these are mostly subjective in nature. So if they are giving a problem related to this kind of concept, then most probably they will give the equation of this Nusselt number. Like we know for pipe flow, and if there is a turbulent flow through pipe, then Nusselt number is equal to 0.023 RE power 0.8 and PR power n. So these things we have discussed. So you remember in 2 slides I have revised all of these formulas and values for flat plate in 1 slide. In last lecture I did this, and for pipe flow in 1 slide I have given all of these formulas. So you can make short notes of those slides and you should remember these formulas. So if they are asking a question related to these concepts, you will easily solve those questions. So in today's lecture, in this lecture we will start the 4th and the last chapter of this heat transfer, and it contains radiation and heat exchangers. So again, both of these topics are very important from gate point of view. So from radiation you can expect 1 2 mark or 1 mark question, and from heat exchanger also you can expect 1 2 marks question. So these both topics are very easy. The chapters are small also. This is not lengthy like the conduction and convection was. So by studying small things or less things, there is a high chances of getting more score. So these chapters are very important, so please pay attention while I am teaching these chapters. So let's discuss the contents of this chapter. What are the topics that we are going to discuss? So first of all we will discuss the basics of radiation. So to develop this subject, this is very important to discuss the basics of radiation. So there are some laws related to radiation. So like Planck's law, Wien's displacement law, Stefan-Boltzmann law is there. So we will discuss those laws related to this radiation. Then this topic that you are seeing here, the shape factor. This is very important topic from gate point of view. And 90% of the times, if in gate they are asking a question from radiation chapter, then they will ask question from this shape factor itself. So this is very important topic, and I will discuss this topic very neatly, and you should focus and you will be able to solve questions related to this shape factor. Then this topic, radiation between two large parallel surfaces. Like there are two parallel surfaces, then we have to calculate the heat transfer between them. So this is also very important topic from GATE examination point of view. So after finishing this radiation, we will come to heat exchangers. So first we will see the classification of heat exchanger. So sometimes you may expect 1 mark question from this, but this is very rare because in GATE examination normally they are interested in concepts and numericals itself. So after discussing this classification, we will come to this LMTD and NTU method. So this is logarithmic mean temperature difference, and this is NTU, number of transfer units method. So these are two methods. There are two methods to calculate the effectiveness of heat exchanger and the temperature differences and heat transfer eventually. So this is the course content for this chapter number 4. So now let's start radiation first. So you may remember in chapter number 1 itself, when we were discussing radiation in brief, I discussed these things. So there is a Provost law. So I did not tell you the name of this law in chapter number 1. So now I'm telling this is Provost law, and you have already discussed this law. So every substance above absolute 0 Kelvin. So if there is any substance whose temperature is greater than absolute 0 Kelvin, so you may know it is impossible to reach below 0 Kelvin. So no one has reached till now below 0 Kelvin. So this sentence can be modified, and it can be said that every substance emits radiation. Because what this sentence is saying, every substance above absolute 0 Kelvin emits radiation. So there is no possibility of reaching below 0 Kelvin. This is the second law of thermodynamics also. We cannot reach below 0 Kelvin. So you can prove these things with Clausius and Kelvin-Planck statement. So I'm not going to discuss those things because they are the part of this thermodynamics. So we can say every substance in this universe emits some radiation. So these radiations are in the form of electromagnetic waves. So what are these electromagnetic waves? These are the swarms of photon or group of photons. And these photons are small packets of energy or quanta of energy. So these radiations are in the form of these electromagnetic waves. So we already know these electromagnetic waves travel with the speed of light, which is equal to 3 into 10 to the power 8 meter per second. Right. And we know these waves are categorized with respect to their wavelengths. So there is a large spectrum of waves, and let us say this is the wavelength of these waves. Let us say this is 10 power minus 6 micron. This side let us take 10 power 6 micron. So in this range, if a wave is having wavelength of 0.1 micron to 100 micron, then these kind of waves result in thermal radiation. So not all waves are resulting in thermal radiation. So the range of thermal radiation is 0.1 micron to 100 micron. So they can ask this in 1 marks. What is the range of thermal radiation? What is the range of wavelength? Now this is the most important point that we have already discussed. In conduction, we need a material medium. In convection also, we need a material medium. But no material medium is required for radiation. Like conduction, we need mediums which are in direct physical contact. Let us say these are two plane slabs. So if they are in direct physical contact, there will be conduction. In convection, we need some fluid medium. Those fluid particles should move and carry heat. But in radiation, there is no requirement of any material medium. So without any material, the radiative heat transfer can occur. And in fact, this radiative heat transfer is most effective in vacuum. So this is very effective in vacuum. Correct. So these are the basics. So now we will see the properties of radiation. So let's consider there is a slab or there is a substance and some radiation is falling on it, or heat in the form of radiation, in the mode of radiation is falling on it, and the magnitude of this heat is Q0. So Q0 is falling on this surface. So what are the possibilities? What can be happen to this heat? So the first possibility is this energy can be reflected back in another direction. So let us say this is reflected back, and let us denote this reflected heat by QR. So R is for reflected. What is the second possibility? This body can absorb some of the heat because it has some specific heat or heat capacity, so it can absorb some of the heat. So absorbed heat, and let us say this absorbed heat we are denoting with QA. So this is the absorbed amount of heat. Now the third possibility is it will transmit the heat, like we discussed in the second chapter, the conduction. If some heat is coming from this side and from this surface, some amount of heat will leave from this subject, and if it is steady flow, then if heat entering is Q1, then heat exit will also be Q1. Like, so here let us say this is the transmitted heat. So out of the total incident heat, some of the heat is reflected back, some of the heat has been absorbed, that is QA, and some of the heat has been transmitted. So let us say this transmitted heat is denoted by QT. Now we can write down this equation. Q0 is equal to QR plus QA plus QT, because this Q0 will be a summation of all of these three heats. Right. So this is a heat balance. Now this QR is reflected, as I told, QA is absorbed, and QT is transmitted. Now let us divide this equation with Q0. So divide everything with Q0. So what will happen? This term will become 1. This will become QR by Q0 plus QA by Q0 plus QT by Q0. Now what is the importance of this equation? Let us say this Q0 was equal to 100. So 100 watt was entering to this body, and let us say 20 watt was reflected back, 50 watt was stored, and 30 watt was transmitted. So we can write this equation 100 equal to 20 plus 50 plus 30, right? So it is 100 also. Now if we divide with 100 itself, it will become 1. It will become 20 by 100 plus 50 by 100 plus 30 by 100. So this will be 0.2 plus 0.5 plus 0.3. So what is this showing? This is showing the fraction of heat that has been reflected out of the total incident heat. Right? So this QR by Q0 term, which is denoted by this rho, this is called reflectivity. This is called reflectivity. So what reflectivity represents? The fraction of heat that is reflected out of total incident heat, or Q0. So like in this case we saw rho value will be here 0.2. So it is fraction, so it will be in decimals. So like it is 0.2, and in our example this alpha value. So what is alpha? This is Q absorbed divided by Q total. So alpha is fraction of heat that is absorbed out of the total incident heat. So alpha is known as absorptivity. So alpha will represent the capacity of the body to absorb heat, right? Rho will represent the capacity of the body to reflect it, and similarly this tau will be Qt by Q naught, and it will represent the capacity of the body to transmit heat, right? So all these alpha, rho and tau are in fraction, and as we have proved, always this alpha plus rho plus tau will be equal to 1. Right? Now let's see different kind of bodies that are in heat transfer. So in case of solids and liquids, see the transmissivity in case of solids and liquids are very less. Okay, this is very less. And these kind of bodies are known as opaque bodies, in which the transmissibility tau is very less or tends to 0. So we consider in case of solids and liquids, this tau is 0. So what will happen? Alpha plus rho plus tau is 1. It is the generalized equation. So if tau is 0, alpha plus rho equal to 1 for solids and liquids. Now for gases, as you know, these gases are very poor reflectors. So if there is some gas and some light is coming, so this light can easily pass through these air particles. So this will not reflect back, right? So reflectivity is 0, that is rho is 0. So we can write alpha plus tau equal to 1. So this is for gases. Now this is very important. In heat transfer subject, you will come across black bodies, white bodies, and grey bodies. So what do we mean by these black, white and grey bodies? Is it like if a body is black in color, then can we call it a black body? No, this has nothing to do with color. Color of the body has nothing to do with these black, white and grey. So we will discuss what is the meaning of a black body, what is the meaning of a white body, and what is the meaning of a grey body. So let's see this black body. So I will call a body a black body if it absorbs, let us say Q naught is entering, and if it absorbs all of the heat. So it is neither reflecting nor transmitting. So if Q naught is equal to QA, then these kind of bodies are known as black body. So you may know these concepts also, that in summer days we avoid wearing black cloths, right? Because that is a black body and that absorbs maximum amount of heat. But it is not true that only color has to do with black body. Because, for example, okay, next slide I will tell you why color has do nothing with black body. For now you understand this. If all of the heat is absorbed, then that kind of body will be known as black body. And in that case, what will be reflectivity? It will be 0. Transmissivity will be 0. And alpha will be equal to 1. So for a black body, it is a perfect absorber of heat, and alpha value is equal to 1, rho is 0, tau is 0. So let us take an example of black body. A spherical container with very small opening. Consider this is a spherical container and the opening is very small, and some light is coming inside it, some ray is coming. So what will happen? Let us say there is a very small opening, some light is coming, so it will reflect back, it will come to this. So whatever reflection is occurring, it is occurring inside of the body itself. So if a ray wants to leave this body, there is a very small opening and there is very less probability that the ray will be reflected back, okay, or reflected out of this body. So that's why we will say rho is 0. Don't think that, oh, the rays are reflected back na here, so why the rho is 0? Because from where the entering this rays, from where it is entering, there will be no reflection. So if a ray wants to go out, it has very small opening, and the probability for this ray to go out of this spherical container is very, very less. So we can say all of the radiation will be absorbed here and alpha will be equal to 1. So this is a example of black body, and it is not necessary that this spherical container is black in color. So this is not required, this container to be black in color. Still this is a black body because it is absorbing almost all of the radiation. Now there is one more important point about this black body. This black body emits maximum radiation as compared to other bodies. So it is a perfect emitter. So if you see in Stephen Boltzmann law, we have seen in first chapter, the emissive power of a black body is equal to sigma T power 4. Okay, so if you don't remember, or even if I have not discussed, so this is the emissive power of a black body. So this is from Stephen Boltzmann law that we will discuss later. So for black body, this power of emission is maximum. So black body is known to be a perfect emitter and a perfect absorber also, because we have seen why it is a perfect absorber. So this is about black body. Now let's see white body. So the property of white body is, if some heat is incident on it, it reflects almost all of the heat back. So if it reflects back all of the heat, so QR by Q naught is equal to rho, and here rho will be equal to 1, tau will be 0, alpha will be 0. So as I have discussed, color of the object has nothing to do with the black or white body. So the best example is snow. So let us say on Earth's surface there are some snow particles. So how do they appear? What is their color? What is the color of snow? It is white only. But when sunlight falls over it, it absorbs almost all of the radiation. So its absorptivity is very, very high, and for snow the absorptivity is around 0.96. So alpha value is around 0.96, and from heat transfer point of view, is it a white body? No, it is a black body, because it is absorbing almost all of the radiation. So when it will be a white body, if a body is reflecting almost all of the radiation incident upon it, or the value of rho is 1, then this body will be taken as white body. So this is very important point. Snow is a black body, while color of the snow is white. So it appears white in color, but it is a black body. Okay. Now we will discuss the Planck's law. So this Planck's law is the most basic law of radiation, and all of the other laws have been derived from this Planck law. So this is the base for radiation, and this Planck's law gives the monochromatic emissive power of a black body. So what does it give? It gives the monochromatic emissive power of a black body. So what do we mean by monochromatic? Monochromatic means at a particular wavelength. So this mono means single, and chromatic, it represents the wavelength. So at a particular wavelength, let us say lambda, what will be the emissive power? So So with E we denote emissive power, and if we are writing EB, it is the emissive power of black body. Right. So emissive power of black body, and this emissive power of black body formula is sigma T power 4 that I told you. So later, after this law, the Planck's law, someone differentiated this and he calculated this sigma B is equal to sigma T power 4, and we will discuss this in later slides. Okay. So this law is given by Planck's law, and it gives the monochromatic emissive power of a black body, and according to this law, the monochromatic emissive power of a black body EB at a particular wavelength lambda is equal to C1 lambda to the power minus 5 divided by exponential C2 by lambda T minus 1, where C1 and C2 are some constants. Lambda is the wavelength and T is the temperature. Okay, so you need not to remember this equation. We are just discussing the basics which are required. Now see, this is Stephen-Boltzmann law. So as I told you, in Planck's law, we get the monochromatic emissive power of a black body, or the emissive power of a black body at a particular lambda. But if we want this emissive power over all wavelengths, right, I don't want this at a particular lambda, I want this over the all spectrum of the wavelengths, then we have to integrate this equation from a wavelength with respect to lambda from 0 to infinity. So this law gives the total emissive power of a black body at a particular temperature. So this total means summed over all wavelengths, as I told you, over all wavelengths, right? So EB lambda can be integrated with respect to lambda from 0 to infinite, and after doing that we get the emissive power of a black body is sigma T power 4, right, where sigma is the Stephen-Boltzmann constant. So it is a Stephen-Boltzmann constant, and value of this sigma is 5.67 into 10 to the power minus 8 watt per meter square Kelvin power 4. So this you have to remember. So this is easy to remember also, right? See, 5.67 into 10 to the power minus 8. So this is in series 5, 6, 7, 8. Right? So by this logic you can remember this. And this emissive power of a black body is equal to sigma T power 4. So what will be the unit? It will be watt per meter square. Because sigma unit is watt per meter square Kelvin power 4 multiplied by T power 4, that is Kelvin power 4. So this Kelvin power 4 and Kelvin power 4 will get cancelled. So you will get watt per meter square. So this is the emissive power of a black body. Remember this, sigma T power 4. Now let's see what are the observations that we can see from Planck's law. So in Planck's law, what do we get? Monochromatic emissive power of a black body, which means emissive power of a black body at a particular wavelength. So if we draw the emissive power of a black body over all wavelengths, so we will get these kind of curves for different temperatures. So let us say at temperature T1 we are drawing the monochromatic emissive power of a black body in y-axis, and in x-axis we are showing the wavelength. So this kind of variation that we see. So at temperature T1 this is the variation, at temperature 2 we get slightly higher. So this is for T2 and this is for T3. So T3 is greater than T2 is greater than T1. So this is the graph between monochromatic emissive power and the wavelength, right? So let us see. So these are the peak of these curves, right? So let us say here this is the peak of this curve, this is the peak of this curve, and this is the peak of this curve. So what this peak is showing in y-axis, it is showing the maximum emissive power. So at this point, because let us say at this point this is the emissive power, at this point this is the emissive power at temperature T3. So at this point the emissive power is maximum at temperature T3. So this point is showing maximum emissive power at a temperature T3. So here this is the maximum emissive power corresponding to temperature T2, and this point is showing the maximum emissive power corresponding to temperature T1. Now the corresponding wavelengths, because this is the maximum emissive power, and when you plot to the x-axis you will get a wavelength. So this wavelength is denoted by lambda 1 max for temperature T1, lambda 2 max for temperature T2, and lambda 3 max for temperature T3. So what is the significance of this lambda? It is the wavelength corresponding to the maximum emissive power. So see, this wavelength lambda 1 is corresponding to what? It is corresponding to the maximum emissive power, where at temperature T1. So for lambda 2 max, what can we write? It is the wavelength corresponding to maximum emissive power at a temperature T2. Similarly, lambda 3 max will be the wavelength corresponding to maximum emissive power at temperature T3. Now, as we know from our concepts of maxima and minima, if you want to find out a maximum or a minimum of any function, because here EB lambda is a function of lambda, right? So if you want to find out the maximum of this value, what do? We differentiate this with respect to lambda and equate it to 0. So when we do like this, we get this equation, lambda t is constant, or we can say lambda max into t is constant. Like so, this is a Wien's displacement law. So Wien's gave this law. So this is known as Wien's displacement law. So it also, what is the significance of this? Let us say you increase this temperature, right? So to maintain this value constant, what will happen? This lambda max should decrease, right? So lambda max into t is constant. So if you are increasing one of the factor, then other factor should decrease. Now come to this diagram. This is for T1, T2 and T3, where in this direction the temperature is increasing. So let us say at T1 this was the lambda max, right? Now let us say I'm increasing this temperature and we are going to T2. So when we are going to T2, you can easily observe this lambda max value has been decreased. So from here it is shifting on this side. So Wien's displacement law is talking about displacement of this lambda value itself. So as you are increasing this temperature, this lambda max value, or the value at which the maximum emissive power will come at a respective temperature, so this lambda max value keeps on decreasing. Now from here also, if you increase this temperature, then this peak is coming here, so this lambda max value is again decreased. So the displacement of lambda max value. So lambda max 1 is greater than lambda max 2 is greater than lambda max 3, right? So this is the displacement of this lambda max, and this law is known as Wien's displacement diagram or Wien's displacement law. So sometimes they can give you a value of lambda max, let us say 5 micron, and temperature they can give 300 Kelvin. Then they will give another temperature, let us say 500 Kelvin, and they will ask what is the lambda max value. So what do you have to do? 5 into 300 equal to 500 multiplied by lambda max. So from here you can calculate this lambda max value. So Planck gave this law but it was Wiens who actually understood this. Alright, so this is very important observation from Planck's law. Okay. So now let us discuss some of the properties of radiation. The first one is irradiation. So irradiation is nothing but whatever radiation that is incident on the surface. So just for convenience, we are calling it with a different name, that is irradiation, and it is denoted by capital Z. Okay, so this is irradiation. Now this is very important property, the emissivity. So emissivity is denoted by this epsilon, and it is the ratio of emissive power of a body. So I told you emissive power is denoted by small e. So this emissivity epsilon is the ratio of emissive power of a body to the emissive power of a black body. Okay. So it is defined as the ratio of emissive power of a body to the emissive power of a black body at a temperature T, obviously, at a fixed temperature T. Now, if you want to calculate the emissive power of a body, so just do the side chain. It will be equal to epsilon into sigma EB, right? Not sigma EB. And we already know EB is equal to, or emissive power of a black body is equal to sigma T power 4. From Stephen Boltzmann law, we have derived this by integrating this EB lambda with respect to lambda from 0 to infinity, right? So sigma value also you know. So by doing this, you can easily say that emissive power of a body or a non-black body, emissive power of a non-black body will be equal to its emissivity, which is a property of material, multiplied by sigma T power 4, right? So if it is a black body, then emissive power will be sigma T power 4, and if it is a non-black body, then it will be emissivity into sigma T power 4. So this you have to remember, this is very important. And there is one more important point, as I told you in one of the slides, that black body is the perfect emitter and perfect absorber. So if it is a perfect emitter, its emissivity will be equal to 1. Or in this formula also you can say, in place of emissivity we have kept 1 in black body, right? So emissivity of black body is equal to 1. So no need to write this, I'm just telling you. So for a black body, emissivity is equal to 1, absorptivity is equal to 1, reflectivity is 0, and transmissivity equal to 0. Fine. So this is the emissivity. It is the ratio of emissive power of a body to the emissive power of a black body. And if you are asked to calculate the emissive power of a non-black body, then it will be the product of its emissivity into sigma into T to the power 4. Okay. So let's move forward. So the reflection that we have talked about in previous slides, that if some heat is incident, let us say Q0, then QR heat is reflected. So this reflection is also of 3 different types. So there are 3 types of reflections. What are those? First one is specular, second one is directional, and third one is diffuse. So what happens? Let us say some reflection. Let us say this is the y-axis. Let us say some heat is coming or some ray is coming to this body and it is making an angle of theta with y-axis. And let us say the reflected ray is also making an angle of theta from the y-axis. Then this kind of reflection is known as specular reflection. Right? So this is the first one, specular reflection, in which the incident angle and reflection angle are same. Now the second one is directional. So in directional reflection, let us say this heat is coming, this ray is coming, and it has been reflected in three different directions, and the properties are different in different directions. So the radiation properties these depend on direction, on the direction of ray or direction of reflection. So with respect to the direction, see this red one, green one and blue one, these are having the different radiation properties. Let us say R1, R2 and R3. R is the radiation properties. So this kind of reflection is known as directional reflection, in which radiation properties depend on direction. Correct? So now third one is diffuse, and in diffuse radiations, the radiation properties are independent of direction. So here you can see this ray was reflected in three different directions, and the properties are same for each direction, R, R and R. So radiation properties are independent of direction. Okay, so these are the three kinds of reflections. So for theory question, this kind of things are important. So once or twice they have asked in GATE examination about these concepts. Now we have seen the black body, for which the alpha is 1, we have already seen. White body, we have seen the rho is equal to 1. So we have discussed what are black bodies and what are white bodies, and we have seen there is nothing to do with the color of the body. Similarly, we will see gray surface in this slide. So surface is known to be gray surface if the properties like emissivity, alpha, rho, tau or any radiation property, these are same or not changing with respect to wavelength. Or the properties of radiation are independent of wavelength. So let us say we draw property of wavelength in y-axis, let us say the emissivity, and in x-axis we are drawing this wavelength. So if we draw this for different bodies, we know for black body the emissivity is maximum. The value of emissivity is 1, right? So we have shown for black body it is 1 and it is not changing with wavelength. So at any wavelength, at any lambda, the emissivity of black body is how much? It is 1. So for black body this is. Now for gray body, we have seen the emissivity, absorptivity are independent of wavelength. So this line is for gray body, and for gray body the emissivity is not changing with wavelength. So it is a straight line. I'm sorry, there is some zigzag, but this is a straight line. And for a gray body, the properties are independent of wavelength. Independent of lambda, right? Now let us say there is a real body. So for real bodies, the properties will change with lambda. So let us say there is a variation. So for at this wavelength, the emissivity is this much. At this wavelength, the emissivity is this much. So it is changing continuously with the wavelength. So what is the assumption? For gray body, properties are independent of lambda. But there is an important point. There is no surface which is truly diffuse or gray. So in case of diffuse, what happens? The reflected rays, they have same property in all direction. So diffuse, that means no dependency on direction, and gray means there is no dependency of lambda. So in our further studies of radiation, we will consider the surface is diffuse and it is gray. So it simplifies our analysis, but in reality there is no surface which is truly diffuse and truly gray. Okay. Now there is one more important law, Kirchhoffs law. So read the statement. According to Kirchhoffs law, under thermal equilibrium, the ratio of emissive power of a body, that is E. So the ratio of E and its absorptivity alpha is constant. Right. So Kirchhoffs law says that E by alpha will be constant for any body. Right, under thermal equilibrium. That means there is no temperature difference between the bodies, then E by alpha will be constant. So E by alpha we can write down E1 by alpha 1. So for black body also EB by alpha B. So all of these things will be constant. And we already know this alpha B, that is the absorptivity of a black body. So how much is the value? We all know for black body the absorptivity is 1. Right. So now take these equations, the first one and the last one. So what do we get? E by alpha equal to EB by alpha B, where alpha B is 1. So this can also be written as E by EB equal to alpha by 1, or E by EB equal to alpha. Now what is this E by EB? This is the emissivity. So we have defined emissivity as it is the ratio of emissive power of a body to the emissive power of a black body. So from Kirchhoffs law we get this equation. Emissivity is equal to absorptivity under thermal equilibrium. Okay, so this is also a very important law, Kirchhoffs law, and according to this emissivity is equal to alpha. So hope you followed how we started. We started with E by alpha equal to constant. Then for two bodies we wrote this equation E by alpha equal to E1 by alpha 1, and it will be equal to EB by alpha B also. So alpha B value is 1. So when we take these two equations, then we get E by EB equal to alpha by alpha B, and alpha B is equal to 1, and E by EB is defined as emissivity, that is epsilon. So this epsilon will be equal to alpha, and emissivity is equal to absorptivity. So this is the Kirchhoffs law. Now this concept is very important from the GATE point of view, as in the starting of chapter itself I told you the shape factor. This is also known as view factor. This is also known as geometric factor. So these are, or this is the very, very important topic from GATE point of view. So what is a shape factor? So consider there are two bodies. This is the body number 1 and this is body number 2. So we all know that every body which temperature is greater than 0 Kelvin emits radiation. So let us say this body also is emitting some radiation in all directions. So this is emitting the radiation, and consider in its neighborhood. So this is body number 1, and in its neighborhood there is one more body, body number 2, and this is in the neighborhood of this body. So let us say, because this body is emitting some radiation and body 2 is in its neighborhood, so obviously some of the radiations will fall upon this body number 2. So is it possible that all of the radiation from body 1 will fall upon body 2? No, because of this kind of orientation, only some of the radiation of body 1 can reach to the body 2. Because some are going in this direction, some are going in this direction, right? So only some of the radiation will reach to body number 2. So the radiation which was emitted from body number 1 and it is falling on body number 2. So the fraction of radiation emitted from 1 falling on 2 is known as the shape factor of body 1 with respect to 2. Right. For example, if this body 1 is emitting 100 watt of radiation, right? So it is emitting 100 watt in all the directions. Okay. But let us say due to this shape and this orientation, only 20 watt out of this 100, only 20 watt is falling upon 2. So we want to find out how much fraction is falling on 2. So how much fraction is falling on 2? It is 20 divided by 100. So it is 0.2. So in that case, F12 or the shape factor of 1 with respect to 2 will be equal to 0.2. And how do we read this F12? The fraction of radiation of 1 that is falling on the surface 2. Okay, so the fraction of radiation of 1 falling on 2 is known as F12. Now let us say if 2 is radiating and 1 is in its neighborhood. So if you want to find out how much fraction of radiation of 2 is falling on 1, then it will be F21. So fraction of radiation of 2 that is falling on 1, right? So this is denoted by F21. Now can you tell me what is F11? It is the fraction of radiation of 1 falling on 1 itself. Let us say there is a concave surface. So in this case we have considered the outer surface of this body, right? Let us consider the inner surface because both the surface will radiate. So it is the inner surface, surface number 1 let us say, and if it is radiating, so obviously you can see these rays are striking to this body itself, right? So the radiations are leaving from 1, falling also on 1. So this is known as F11. So the fraction of radiation falling on emitted from 1 and falling on 1. Right. So in next slides it will become more clear. So this is very important point. The shape factor depends only on geometry and orientation. So if orientation and geometry of this body will be changed, the shape factor will be changed. So it has nothing to do with surface characteristics and temperature. Right. So shape factor is only depending on this geometry. Now there are some important theorems related to this shape factor. Let us say there is a body 1 whose surface area is A1, right? And there is a body 2 whose surface area is A2. Now this body 1 is radiating heat, and let us say the radiation emitted from 1 and falling on 2 is F12, and radiations emitted from 2 and falling on 1 is F21. Then there is a reciprocity theorem, and it states A1 F12 is equal to A2 F21. So how this can be written? A1 F, so this is 1, so this will also be 1. A1 F12 equal to A2 F21. So this is the reciprocity theorem. So when we will solve the numericals, we will use this theorem. So you have to remember this, A1 F12 equal to A2 F21. Now summation rule. So this is the second rule related to this shape factor. So what is the meaning of this summation rule? Let us say there are n surfaces in a body. Let us say this is a rectangular cross section duct. So how many surfaces will it have? It will have 6 surfaces, right? So this is surface number 1. Opposite to this, let us say this is surface number 2. This top surface, let us say it is 3. Opposite to this bottom surface will be 4. Right, this surface which is on the right side is 5, and opposite to this, the left hand surface, it will be 6. So there are 6 surfaces, and we can write this summation rule like this. Let us say F11. So let us say we are considering the surface number 1. So whatever radiation that is emitted by 1, so let us say it is falling on 1 itself, it will fall on 2, it will fall on 3, 4, 5 and 6. So radiation of 1 falling on 1 plus radiation of 1 falling on 2 plus radiation of 1 falling on 3 plus radiation of 1 falling on 4 plus like this, F15, F16 must be equal to 1. What is the meaning? These total should be equal to 1. Let us say this 2 received, let us say F12. What does it represent? The radiation emitted from 1 and striking surface number 2. Let us say this fraction is 0.2. So like this, the values of these things, the summation should be equal to 1, because it will strike each of the surfaces, right? So fraction should be, summation should be equal to 1. So this is the summation rule. So if there are n surface, then it will be F11 plus F12 plus F13 plus dash 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 dash. So you have to continue like F14, F15. So it will be continue to F1n must be equal to 1. Right. So this is the summation rule related to this shape factor. Now there is one more important point. For flat and convex surfaces, the self-view factor is 0. What is the meaning of this self-view factor? Self-view factor means shape factor of 1 with respect to 1, or shape factor of 2 with respect to 2, or shape factor of 3 with respect to 3. Self-view factor means radiated by 1, falling on 1. So right, let us say this is a surface number 1, the internal surface. So radiated by 1, falling on 1. So it will show the self-view factor. Similarly, radiated by 2, falling on 2. Radiated by 3, falling on 3. So this is the self-view factor, or in general terms, it can be written as FNN. So this self-view factor is FNN. Right. So what he is telling, for flat and convex surfaces, the self-view factor is 0. So let us consider first this convex surface. So the outer surface of this sphere, let us say sphere. So the outer surface is the surface number 1, and it is a convex surface. So for this convex surface, let us say some radiations are leaving this surface. So in whatever direction they are leaving, they will not strike back this surface, right? So whatever direction they are leaving, they cannot strike back to this surface. So F11 will be equal to what? It will be equal to 0. Similarly, for a flat surface or a plane surface, in whatever direction they are leaving, they cannot strike back to this surface number 1. Unless they are reflecting from other surface, they will not strike back. So F11 equal to 0 here also. Right. But let us say take a concave surface. So the same sphere, but the internal surface of it. Let us say surface number 2, the internal surface of an sphere. So in this case, let us say this is striking, this is emitting some radiation. So this whole surface is 2 itself. So it will strike on 2 itself, right? So F22 in this case is not equal to 1. Or if you are considering this as 1 itself, then F11 is not equal to 0, right? So F22 is not equal to 0. So these are the basic things about the shape factor. So for today's lecture, the time is not enough, so we will stop here. So in next lecture, we will do some problems related to the shape factor, because this is very important to solve the problems just by knowing the theories we cannot do anything. So we will do some problems related to shape factor, and then we will see the equations of radiative heat transfer for different cases, like a small body kept inside a big room, a large room, or the heat transfer between two large parallel plates. So these things we will discuss in the next lecture. So for this lecture we will stop here. Thank you very much.